All right, let's talk about something that could genuinely change everything: nuclear fusion. We're going to break down what it is, why it's been so unbelievably hard to get right, and why, after decades of promises, it might, just might, be getting close. For as long as I can remember, nuclear fusion has been this running joke in science, right? It's always 40 years away. But this quote, this one really hits different. It's from MIT physicist Dennis White, and it perfectly captures this massive shift that's happened. The old timeline, it's gone. Something fundamental has changed, and the race is well and truly on. So, what is this incredible thing we're trying to unlock? Well, it's not just another power source. It's basically the engine that runs the entire universe. So, at its most basic level, fusion is what makes the sun and all the stars shine. You take really light elements, like isotopes of hydrogen, and under just ridiculous amounts of heat and pressure, you force them to slam together and merge into a heavier element, like helium. And when that happens, a tiny little bit of their mass vanishes and is converted into a huge amount of pure energy. Yep, that's Einstein's famous E=mc² in action. Now, it is so easy to get fusion mixed up with its more famous, or infamous, cousin, nuclear fission. But here's the key thing to remember. They are complete opposites. Fission, which is what our current nuclear power plants do, is all about splitting heavy, unstable atoms like uranium apart. Fusion does the exact reverse. It builds atoms up, fusing light ones together. And here is why that difference is so important. Look at this number. Per reaction, fusion unleashes about 10 million times more energy than a chemical reaction, like burning coal or natural gas. I mean, just think about that. It's why we call it the ultimate energy source. You physically can't get more energy out of less stuff. And the benefits, they sound like something out of science fiction. The fuel comes from water, so it's practically unlimited. It produces zero greenhouse gases. The process itself is inherently safe. It can't have a runaway reaction or a meltdown. If anything goes wrong, the whole thing just stops. And it creates barely any long-lived radioactive waste. I mean, come on, it is the absolute holy grail of clean energy. Okay, so that leads to the big question, right? If it's so perfect, why don't we have it yet? Well, the answer is that trying to recreate the conditions inside a star right here on Earth is probably one of the most difficult engineering challenges we have ever attempted. It really all boils down to three things that you have to get just right, all at the same time. You need insane temperatures to get the atoms moving fast enough to fuse. You need them packed together densely enough, and then you have to hold it all together long enough for the magic to happen. You nail all three, you get ignition. So let's talk about that temperature. To get fusion going here on Earth, you need to reach about 100 million degrees Celsius. To put that into perspective for you, that is way, way hotter than the actual core of the sun. You need that kind of heat to overcome the natural force that makes these atomic nuclei want to push each other away. Now, at these temperatures, something really wild happens. Matter isn't a solid, a liquid, or even a gas anymore. It becomes plasma, the fourth state of matter. The electrons are literally ripped away from their atoms, creating this super hot, electrically charged soup. This is the stuff that stars are made of, and it's what we have to somehow create and control. And control is the key word. You've created this 100 million degree plasma, but it can't touch anything. If it touches any physical material, it just cools down instantly and the reaction fizzles out. Like one scientist put it, it's just a very hard fire to keep going. And that, in a nutshell, is the challenge of confinement. So, for decades, scientists have really been chasing two main ways to solve this confinement problem. You can almost think of it like a heavyweight boxing match. In one corner, you've got giant magnets, and in the other, you've got the world's most powerful lasers. The laser approach is called inertial confinement, and it's basically a tiny, controlled explosion. You take a fuel pellet smaller than a BB, and you blast it from all sides with nearly 200 of the most powerful lasers on Earth. It crushes that pellet so fast and so violently that the core gets hot enough and dense enough to ignite in a tiny burst of fusion, all before it has a chance to blow itself apart. The magnet approach is completely different. It uses incredibly powerful magnetic fields to create a kind of invisible bottle. This magnetic tokamak, which is usually shaped like a donut, traps the charged plasma particles. It forces them to spiral along the magnetic field lines, holding them in the center, away from the cold walls of the machine. So you can really see the two different philosophies here, right? With lasers, you get these quick, pulsed bursts of energy, creating a super dense but very short-lived state. With magnets, you're aiming for a continuous, steady burn, almost like a furnace, but the plasma itself is much less dense. And here's where the story gets really good, because recently both of these approaches have had game-changing breakthroughs. In late 2022, the laser experiment at the National Ignition Facility did something that had never been done before. They achieved what's called scientific break-even. For the first time in history, they got more energy out of the fusion reaction than the laser energy they put in. It was a huge "we can do this" moment. Meanwhile, in the world of magnets, a team from MIT and a private company developed a brand new type of superconducting magnet, and it reached a field strength of 20 Tesla. That is an unbelievably powerful magnet, the strongest of its kind ever made. And that is the key that unlocks designs for fusion reactors that are much smaller, cheaper, and more powerful than we ever thought possible. So these two huge scientific wins have lit a fire under a whole new kind of race. We've moved beyond the academic question of, is this even possible, to the much more exciting engineering question of, okay, how fast can we actually get this on the grid? And you can just see it right here. The timeline is getting crushed. That old joke is officially dead. With scientific break-even in the rearview mirror, we now have multiple teams, both public and private, who are seriously targeting the early 2030s to build the very first pilot plants that will actually generate electricity. And that's because the entire landscape has been transformed. Fusion isn't just for massive government labs anymore. A whole commercial industry has exploded onto the scene, with dozens of startups backed by billions in private investment. And they're all competing to see who can be the first to deliver commercial fusion power. You know, it really feels like we're living through one of those major turning points in history. It's like the science historian James Burke said, our whole world changes when we have a fundamental new insight. And the insight that we might actually be able to build a star on Earth, well, that's about as fundamental as it gets. So that's really the incredible question we're left with. Think about it. We only figured out how stars actually work back in the 1930s. Less than 100 years later, the science, the technology, and the willpower all seem to be coming together. So are we really on the verge of building our very own star right here on Earth? It's an amazing time to be alive. Thanks for watching.